A wave is a disturbance in a medium, and you can see the direction in which the wave is moving. It's along the positive x-axis. Like I explained to you, you can already see the wavelength, you can see the crest, you can see the troughs, the amplitude, the meaning of one cycle. Everything is clear from there. This is what I've been trying to explain, and a little bit more. I did explain more than this. Okay. It's always interesting to ask a student, how do you come up with this formula? Because you cannot derive this formula, it's just logic. Can somebody tell me how you get this formula? And that's wave velocity. All right, what's the angle between particle velocity and wave velocity? 90 degrees. Because the particle is moving up and down along the y-axis. Are you with me? But the energy is moving along the x-axis. This subject is easy, and people don't believe me. And this kind of a wave is called a progressive wave. What do you mean by the word progress? Means moves outwards into the material and doesn't come back. Just like if you take a stone, you have nothing else to do one fine evening, maybe you're depressed, I don't know, and you sit by the side of a pool of water and drop a stone into it. You know, people do that sometimes. Huh? At the top, the stone has potential energy. As it falls, it changes into kinetic energy. Just before hitting the water, all of its energy is kinetic, right? But at the moment it hits the water, the stone or whatever you dropped gives its energy to the water molecule that it hits. What does the water molecule do? Nature is not selfish like us. So it decides to share the energy. So it says, oh, I got it. It's not going to say, I'll put it in my pocket. It's going to say, let me share it. And so it begins oscillating and then sets the next one oscillate. Can you see it? I want you to see it. And you see that every particle is oscillating. But in actual life, the first particle will oscillate with a maximum amplitude, isn't it? Because of damping, the oscillations will die out. But if there was no damping, wouldn't every particle oscillate with the same amplitude? Come on. Now, can you really see the difference between particles moving and energy moving? And do you see what a progressive wave is? I hope so. But there are two types of progressive waves. This is called a transverse progressive wave. Transverse. Why? Particle moving along the y, energy moving along the x. But you have the second one. It's called a longitudinal wave. That's a tough term. So there are two types of progressive waves. One is transverse. That's the picture of a transverse wave. The second type is, well, this word just means lengthwise. Longitudinal means lengthwise. Best example. Have you heard of a tuning fork? You know what a tuning fork is? Mm-hmm. All right. You will see it in the lab if you have never seen it. You hold it in your hand and make it oscillate. It's going to oscillate this way, isn't it? Back and forth. What's it doing to the air molecules? Each time the prong comes out, it's pushing the air molecules together. Each time it goes that way, it's pulling those air molecules on this side further apart. You got it? So let's study this in slow motion. Each time it moves forward, there's a compression. Each time it goes out, there is what is called a rarefaction. I don't know what your textbook calls it. Let's see. A rarefaction and a compression. Compression means increased density. Rarefaction means decreased density. Does that make sense? So each time it moves, so you see compressions and rarefactions moving out, one after the other. Just like this could be a compression, this could be a rarefaction. See the correspondence between the two? Many times it's very difficult to draw a longitudinal wave, so we always represent any kind of wave this way. But just know that the names are different. This is a crest and a trough if it is a transverse wave. The same points would be called Compression, rarefaction. Sound is a longitudinal wave. Are you hearing me? You know what? Because my vocal cords are vibrating, I can really feel it. The vibration that begins from there, through the air, reaches your eardrums. This is physics. And sets it in a vibration, exactly at the same frequency that it started out. Otherwise, it would have been funny. That's why all of you hear me, even in your sleep, with the same frequency. The same frequency that started out. What kind of wave is that? Is that transverse or longitudinal? Longitudinal. Got it? Okay. And longitudinal waves. There you got it. Yes. Picture should make it even more clear. With a spring, it's even easier to explain. Look, the wave motion in both cases is along the positive x-axis. But you see the names given are P waves and S waves. You see that? P stands for pressure. S. Anybody taken geology before coming to this class? Surely you know about those. P waves are pressure waves and S waves are shear waves. Pressure waves are longitudinal waves. Can you see the compression and the rarefaction? You can see that. And S waves are transverse waves. And how do we know that the core of the earth is in a liquid state? Because somebody dug a hole and went up there and never came back. No. So how do you know that the core of the earth is molten? Because when an earthquake happens on one side of the earth, we still manage to get longitudinal waves on the opposite side. That's scary. On the opposite side. If you're listening to me, you understand. And we know that longitudinal waves can only propagate through a liquid. Did you hear me? In fact, a fluid. So since we get the P waves on the opposite side of the earth, and we do know that longitudinal waves go through a fluid, the earth's center must be in liquid state. Of course, not gaseous state. So, liquid state. We do not get S waves on the other side. What does that mean? That means that S waves can propagate only through a solid. I gave you points. S waves are shear waves. What do you mean by shearing something? Twisting something. Have you ever thought about twisting a liquid? You can't twist a liquid, but you can twist a solid, can't you? So, shear waves only through a solid. So that's why we know that the core of the earth is molten. Because of the P waves. Everything is clear? Wonderful. Present it as a question. All right, what's a transverse wave now? Let's look at it again. A string, one end of it is tightly fixed, and the other end is in your hand, you're moving it up and down. Isn't that a transverse wave? Particles are moving up and down the end. Okay. What happens to the velocity of the wave if I make it tighter? Think. I make it tighter. I stretch it all the more, like I tighten the guitar string. What happens to the speed of the wave? Will it increase or decrease? It's just logic. It'll increase. So surely the velocity depends on the tension in the string, isn't it? Now let's go back and look at the guitar again. You know, at least it has 6 strings. I think classical guitar has more, right? Somebody's been telling me. You know anything about that?
I mean, they have 12-string guitars.
See, that's what somebody told me. So let's just look at a 6-string guitar. What's the difference between the strings? The thickness. So the diameter is different. That means if you take 1 meter of those strings, 1 meter, wouldn't their masses be different? I'm talking about the mass of. That's why some students get confused. Half asleep, they'll hear the word mass. They'll think I'm talking about the mass suspended at the end of the string. No, I'm talking about the mass of the string. I'm talking about the mass of 1 meter of the string. It's called mass per unit length. What's the unit of that? What is the unit of that? We never measure mass in grams. Kilograms per meter. Really, I want you to understand. That's why I'm taking so much time. So that means if you take 1 meter of those strings and weigh them, this is what you're going to do in the lab. And most people don't realize what they do. They just, okay, why? I don't know. Just do it. Go through the motions. You're wasting time. Take 1 meter of this, find the mass. How much do you think it will be? In kilograms, it will be 0.003. Have that idea. So if I come up with somebody giving an answer like 300 kilograms per meter on the lab, it tells me that that person is not even thinking about what they're writing. 300 kilograms per meter for that string. I've seen it. Okay, now tell me this. How does the speed of the wave depend on the mass per unit length? Let's have all those 6 strings under the same tension. Okay? All the 6. Same tension. Which string do you think the wave would travel fastest? Think and tell me.
The little one.
The thinnest?
Why?
But why? All right, let's take a look at the formula. The speed is given by Ft by mu. What's Ft? Ft is the tension. And normally the tension is mg, where you're talking about a mass suspended, right? So the tension is m times g. And mu is not the sound made by a cat. Mu stands for mass per unit length. Mass, that's what I'm writing. Mass of the string divided by the length of the string. That's how you find it. Find the total mass of the string divided by the total length, you will get the mass of 1 meter, wouldn't you? But sometimes, can anybody relate the mu to the radius of the string? Can anybody relate mu to the radius of the string? You have enough time because there's another way I get the exercise. Cleaning the board. Okay. Think about it. What are you thinking? Well, we do know that the bigger the radius, the bigger the mass per unit length. We know that. So if you just imagine that this is 1 meter, and you're trying to find the mass of this entire material. Isn't mass volume times density? Now, how back should I start? Should I start with what density is? I don't have the time. Mass is volume times density. And what's the formula for volume of a cylinder? Isn't this a cylinder? Okay, what's the word?
Cross-sectional area.
Pi, yeah, cross-sectional area, which is pi r squared, times its, which is 1 meter. Because we're trying to find the mass of 1 meter. Okay, so pi r squared times h, which is 1 meter, times density. Who needs the 1? Okay, so you have another formula. So when you work out problems, if you're given the radius, that's how you find the, sorry, don't want you to be confused. That's the mu we are talking about, isn't it? Mu is pi r squared. So, okay. So, that is mu is pi r squared rho. That's the velocity, tension. That is, it's called the linear density. So if you see a word like linear density, then you know it's mu. Mass per unit length. Why is it called linear density? Because it's mass per unit length. What is density? Mass per unit volume. See the difference? That's why it's called linear density. It's measured in kilogram per meter. I've given all the units. We look at the energy of a group of particles. And what kind of group do we take? We want to look at the number of particles in a certain volume. Now, you look at that material that I've tried to draw a little bit more. That's the direction of velocity. Okay, now the picture is complete. I've just taken a section of the material through which the wave is propagating. Can you see that 3D idea now? What is these? I'm going to take the surface area, something like this. I'm going to take the surface area, isn't it? Something like this, as S. And if I multiply it with the length, wouldn't I get the volume? It becomes boring when I have to repeat everything 3 times. You take the surface area and multiply it with the thickness, wouldn't I get the volume? Okay, so right there you can see that the volume is going to be, okay, what's the volume from that figure? S times the length. Oh, what do you mean by length? Velocity of the wave times the time. Because distance is velocity multiplied by time. You see that connection? So we're just looking at a volume of S times velocity times T. That is our volume. Now, what's the formula for energy of a particle? What kind of energy does this have? Isn't it moving? Kinetic energy? What's the formula for? No, wait, does it have potential energy also? In simple harmonic motion? Yes, it has both. We have to take the total energy. Formula for total energy? In simple harmonic motion? 1/2 K A squared. Oh, what's the K? The spring constant. What's the A? The amplitude. So the total energy is given by 1/2 K A squared. Okay, 1/2 K A squared. Everything clear? K is, some people tell me there are too many Ks. Yeah, you need to know the difference. There are too many boys and girls, but you sure know the difference, don't you? Not everybody is the same for all of us. So, same way. K is spring constant. A is the amplitude. What's the formula for frequency? Frequency. 1/2 pi. Just got it. Just finished the semester. 1/2 pi root K by M. Does anybody know the formula for time period? 2 pi root M by K. Frequency is the reciprocal of time period. Okay. That's the formula for frequency. 1/2 pi square root K by M. What's the M there? Mass of? The mango on the tree. No, the mass of the particle that we're looking at, isn't it? Mass of the particle. Can we rearrange that? You know what I'm trying to do? I'm trying to substitute for K. So make K the subject. You go ahead and write it. Square both sides, make K the subject. What would you get? Square both sides. Got rid of the square root. Rearrange. Isn't this what I get for? Isn't this what I get for K? Square root, square it, that's what you get. Plug it back into that, so you get 1/2. I've got to write the whole thing for that, and so now I have energy is 1/2. That's just the energy of one particle, remember. Now I'm going to look at the energy of all those particles. 3D waves, mass is volume times density. Slow down. Mass is volume times density. I've been saying this so many times. Volume is S times the length, isn't it? Where S is the surface area. Yeah, cross-sectional area in this case. Surface area times length. And L is velocity multiplied by time. Therefore, when you plug back everything into this. Okay, I had forgotten to write A squared there. So now I brought it back. Nobody noticed that? A squared has come back now. Wow, very important equation. Now what's on the left-hand side? What's this? I know it's energy. This is the energy in a particular volume, isn't it? Energy in a particular. These are the crucial points. It's not the alphabet. Everybody knows A, B, C, D. It's knowing what each one exactly stands for. E is the energy in a particular volume. Is that clear? These are constants. F is the frequency. A is the... Now, why is this equation important? Because it tells us that a female can make more energy than a male. high frequency. Energy is directly proportional to square of the frequency. Do you see that? So the higher the frequency, the more the energy. Don't ever try to get in a fight with a lady. If they talk, they have more energy. That's the reason. But also, the energy depends on what? Amplitude is just the loudness. Square of the amplitude is the loudness. That's where the male makes up, kind of. Nobody understood anything. So energy depends on the square of the frequency and also depends on the square of the amplitude. A cat's meow, how do you say it? Meow? Mew? Meow? No, whatever. I just wanted you to be awake. And a lion's roar. Which one has a higher frequency? Which one has a higher amplitude? Thank you. If the lion is not too old. You know, at the end of the day, at least people need to know the difference between frequency and amplitude. So sad to say, your education is so messed up sometimes. Walk out with a grade A, do not know. That doesn't happen in physics. That's why I like the subject. Was I recording all this? Difference is coming up. Oh, wait, you already saw the difference. What does that show? The average power. The average power is energy over time. Just remove the time factor and you got the formula for power. Average power. Okay, go ahead. Have you heard of the term called intensity? Intensity. Yeah, that's why we use it. That was so intense. The summer session was so intense. What do you mean by intensity? Intensity is power divided by the area. So intensity is actually energy per second per meter squared. I'm going to say that again. Intensity is energy per second per meter squared. See that? So if you divide this by the area, you get intensity. There you go. Remember, the area is represented by S. Did we? So you divide it by the area, you get the formula for intensity. All right, units. Power. What's the unit of power? Okay, intensity. What's per meter squared? And we're looking at and saying, why should we spend so much time on intensity? Do you want to receive radio waves and television waves in your home? Don't you think that they must have enough intensity to reach your homes or reach our homes? Come on now. That's what we're talking about. We're talking about radio and television broadcasting. So now you see that intensity of a wave depends on what? Hello? Depends on what? You know that each television station and radio station has a definite frequency at which they broadcast. And haven't you heard about short waves and medium waves? Have you? Please. Now you know that if it's a shorter wave, means the wavelength is small, the frequency is big. Hello? So if the frequency is big, it's a short wave radio station and it can travel out to a longer distance. That make sense? But the local radio stations here, I'm not talking about FM. We'll talk about that later on, okay? I'm talking about the longer radio stations. I'm talking about, did you know that there are 3 kinds of modulation? Where am I getting to from this? I'm just trying to connect this chapter to what's coming. They're all connected together. There are 3 kinds of modulation. What is modulation? Modulation is a simple process where if I want to transmit my sound and I do not do anything about it and just transmit it as it is, what do you think about the intensity of the, what do you think about the intensity of my sound wave? Big or small? It'll only go a few meters. Why? Because the human hearing frequency is between 20 hertz and 20 kilohertz. Hello? So the maximum I can produce, if I do, that is 20 kilohertz. Maximum. It won't reach up to 20. It'll become irritating long time before that. On the average, it's like about 8 kilohertz. So that's not much. So if I want my sound to be broadcast, what should I do? I must make it go far distances by modulating it. Okay, what's modulation? I must have a high frequency wave, and then I must somehow mix my sound wave with the high frequency radio wave, mix them up. That process of mixing is called modulation. And then it can go further distances. Why? Because now it's being carried by a high frequency wave. Are you listening? But when it reaches the television, you don't need the high frequency anymore. So there you have to demodulate it. Means you have to separate the audio signal from the high frequency wave. That's called demodulation. Just trying to put something into this class. Are you getting what I'm trying to say? It's like a mom carrying her child to the doctor when the child is sick. Well, only a foolish mom would put an infant on the road and say, go to the doctor. So the mom is the carrier, the high energy thing that carries the child to the doctor. When they reach the doctor, even if the mom is beautiful, the doctor is going to look at the child. Because the doctor does not need the mom now. You know what I mean? That is demodulation. That all make sense? And we're going to get to all that towards the end. So, what we are studying here is connected to electricity, magnetism, electromagnetic waves, radio, television, broadcasting, all of it together. So get ready for the fireworks. Any question on? Now, there's another formula for intensity that's come up here. Just from logic. This is from logic. I just wanted to play completely. There it is. If there's a loudspeaker here, definitely the person that's closer will hear more sound, isn't it? Hello? Yeah. But now the thing is, if there's another person seated at double the distance from the loudspeaker, so there are two people, the second one is at double the distance, what does this formula tell you about the intensity that the second person will get? It tells you very clearly that when the distance doubles, the intensity falls to 1/4. Why? Because the formula for intensity based on distance is given by P by 4 pi r squared. How do you get that formula? What is 4 pi r squared? Of what? Is the surface area of a sphere. All right. So here is the loudspeaker. My big mouth is the loudspeaker now. So isn't sound spreading out in all directions in the form of a sphere? Can't you see that? That's how the 4 pi r squared comes in. Therefore, remember that if you are at double the distance, the intensity becomes 1/4. When we set up our surround systems at home, I don't know, you really have to sit in a particular position to really enjoy the music. Did you know that? If you know that, there's going to be a fight at home. If you don't know that, like in my home, I think I'm the only one. But it's important. Did you get it? And even when you're tuning the surround system, you have a microphone which you have to set up in the beginning and tune it. Nobody's done it? They supply you with a microphone and with a long cable. So you put that microphone exactly at the seat which you're looking for, and then play the speakers, and this one electronically judges the intensity and adjusts the intensity of sound from each speaker. Because they have to be equal, right? What did you shake your head? He's a music man.
What? I mean, he's probably spent a lot of money on. I've never had a microphone.